Just like yesterday, I have the honor of presenting work I didn't do. It's growing into a habit. Maybe you can hire me. I should think about that. Okay, so today I stand here instead of Attila, whom you know, who is the primary author of the Dynalink framework. And I'm going to give you an update on what's new in Dynalink as of JDK 9. Also, there will be a rough overview of what Dynalink is and does and so forth. The usual disclaimers apply. Don't shoot the messenger. Don't ask me anything. We'll see to the possibility of answering questions as they arise. I'm still working on the music. The agenda is simple: overview, advanced, more advanced. I have a mouthful of slides here. It's around 40. So we'll see how far I get and how much of the material I can cover. So let's begin with the overview without further ado. I mentioned yesterday in the talk on NASON and modules that Dynalink is, as of JDK 9, a separate package. It's no longer part of NASON, even though its source code still lives in that repository. But we have a dedicated module in the JDK now. And I'm not going to give the whole story of what Dynalink is and does today, because the story has been told by Attila mostly numerous times in this very place and in other venues. But there are some things that have changed, and I'll focus on those. So first and foremost, API simplification and some streamlining, some work on the class hierarchies. Things are simpler, somewhat more intuitive now, and most importantly, perhaps, the operations are now represented as a type-safe enum instead of strings that need to be parsed and kept around. So, brief recap. Dynalink, it's a library for dynamic linking of high-level operations on objects. Read, write, invoke, whatnot. It's normally used in programming language implementations. The most prominent user is NASON, probably, which is also the context in which Dynalink was developed. And so as soon as a programming language has an object model that might differ from that of the underlying JVM, it might be worthwhile to take a look at Dynalink to take care of the linking of operations at call sites. Also, when there are sometimes implicit type conversions that go beyond what the Java language specification imposes in terms of coercions, Dynalink might be worth a try. Operations in the Dynalink context are call sites, are represented as call sites, and will be linked to some method handle at runtime. It's all dynamic. And Dynalink will take into account whatever contextual information the invocation carries. The usefulness is explicitly not for statically typed languages that have the same object model as the Java programming language itself. It's simply not what Dynalink is supposed to do. Just use the usual bytecode instructions, they will do just fine. But if you have expressions that have a dynamic flavor about them, and I think the examples that we have seen in Jason's presentation on the Scala implementation just now fall into that category, then Dynalink is indeed a good match to address those problems. Up next, a little example from in fact, the Nashorn area. What we see here is 3 Java classes, all of which have a property that can go by the name of color, even though it is implemented differently in each of the classes. We have one field, we have one method that returns a string, and we have one more method that returns an int. So we have 3 different implementations of a property with the same name, essentially. In JavaScript, this code here, which first instantiates one of each of these classes we just saw, and then iterates over those and gets the color property using the same access mechanism each time. This single line, or more precisely, the obj.color bit of the line in the for loop, will boil down to something like the invoke dynamic instruction shown here on the slide. So it's invoke dynamic of something called color, accepting an object, returning an object, and it has a static argument to the bootstrap method that says get property is the operation that's supposed to be run here. So Dynalink used to use strings to encode these operations. So here are some changes. It now uses type-safe operation objects instead of strings, and that has several benefits. For one, both the call-side encoder, that is the compiler that generates the invoke dynamic instruction, and also the decoder, so the bit in the language implementation runtime that guides what the invoke dynamic should link to, are the responsibility of this same language runtime environment. So it makes little sense to forcibly prescribe how it should encode something that it only reads back. And for another, code dealing with operations internally can now work with operation objects instead of parsing all those strings. Finally, the strings had this certain load on the constant pool and also the string intern table at runtime. So, in a nutshell, these composite operations, what used to be this string with the 3 different parts for get property, get element, or get method, is now a composite operation over 3 different constants from the standard operation enum. It's also a named operation. What that is, I'll get to that later. But the core here is it's a composite operation, can be any of these. And those composite operations are used all throughout the Nashorn implementation. The reason is that Dynalink recognizes 3 different namespaces in the standard operations. It's properties of objects, elements of collections, and methods of objects. Conversely, JavaScript objects only have 1 namespace, and Dynalink's composite operations give this OR semantics for attempting operations on all those different namespaces. So this is what's being done here. Bytecode. It's not necessary to use Dynalink in an environment where everything is about bytecode generation. What Dynalink returns as a result of a link operation is a call site. And so they can serve as call site abstractions in language implementations of any kind. An interpreter built on Dynalink only needs call sites with operation encodings, and then appropriate linkers and decoders for these operations. So it could be equally possible to use Dynalink, and the call sites it will return from a linking operation in an AST interpreter or whatnot. Okay, more example coming up. To illustrate the simplest possible use of Dynalink in a language implementation. The characteristics here are the language has its own dynamic expressions, no object model of its own, or any complex type conversion rules. Here we go. It's just part of the runtime, of course, and the details of the decode operation method are left out on purpose, because that's not what we are about here. This is rather about the bits and pieces of the Dynalink framework that are at use. So as explained, I've said that. I will now look at each of the highlighted elements here. So first of all, the bootstrap methods have to return some call site instance. These are generated by a linker. The method responsible for that is called link. And the linker is typically obtained from the dynamic linker factory. As Dynalink expects dynamism to some degree, the root call site abstraction it applies is what we call a relinkable call site. There are different embodiments of that interface. First, there's a simple relinkable call site that's monomorphic and always links to a single target. Now, monomorphic here does not mean that it's fixed once and for all, but that it applies monomorphic caching. So it's a call site that only knows one target, and if the cache misses, it needs to relink. On the other hand, there's a chained call site, which is polymorphic, and this one builds internally a linked list of guard with test handles that is growing as new targets are encountered. So each time the cache misses, there will be a new addition to this list up to a certain degree. Volatile call sites are not offered by Dynalink. It's not part of the system. So a call site, as used by Dynalink, is expressed in terms of a descriptor that consists of a lookup object for context and access checks, an operation describing at a high level what the call site should do, and the type signature of the call site with all the parameter types and the result type that are expected there. The actual Java lang invoke call site objects are all encapsulated inside those Dynalink specific objects and cannot be tampered with in any way. And the descriptor can be extended if the language implementation sees fit. If additional arguments are needed, then the new descriptor implementations can be used. The operation describes what should be done at a call site. So, for example, a composite operation of getProperty and getElement can be used to get an element with a given name from just about any object. And as mentioned, new in JDK 9 is that there is now an enum in place to describe the standard operations. Operations can be composed, and it is possible to have these named operations where arguments are names, example coming up. As an overview of the standard operations that are offered, we have example expressions here in the first column. The second column describes how they are represented as an operation. And on the right-hand side of the table, in the last column, we see what the call site signature looks like. The difference between standard and named operations, if you look at the first two rows, object of x just extracts the property from the variable x, the property with the name given by the variable x. So it's not a named operation. The named operation, one line further down below, object of string foo, that's a named operation where the name itself is bound at the call site. So the name does not depend on any extra variable, which is also why the expected arguments of the named operation only include the object itself instead of the variable and the object. You can think of a named operation as one that binds some of the information at the call site. So here it's the name to be looked up in the object that's bound at the call site, and this operation with this name will be applied to each object subjected to that call. The standard operation for calls is interesting because it requires two operations that are applied in sequence. The method first needs to be looked up via get method, and it can then be invoked with call. Also, the parameters, the arguments for these two operations differ. In the first case, we only need the object. In the second case, we then have to pass the obtained function, the receiver object, and all of the arguments. And again, in the first of these two operations that are needed to issue a call, we can again see that a named operation is used to make sure that the same name is used in all cases. The name is a property of the call site. So far for the operations. Dynalink supports implementing dedicated linkers. So if a language has its own object model or even its own type conversion rules, then an own linker, a dedicated linker, needs to be provided. Up next, a small example for this, and there's a larger example later in the talk, which is about Jython. So bring your own linker. People in the back, is the code visible? Yeah, still okay? Good. So if at any point anything is too small, just raise a hand and let me know. I'll zoom in on details then. Okay, the dedicated linker implements the guarding dynamic linker interface. And as we see here in the red line, a dedicated linker can be added to the set of linkers that are available from the dynamic linker factory. It is definitely possible to have more than one linker in a system. In Nashorn, we use 9 of them. Just to mention a few, there is what we call the beans linker to support accessing properties on Java objects whose API conforms to the Java beans conventions. Then there are linkers for various Nashorn-specific linkage protocols to support access to JS objects, which are JavaScript objects exposed to the outside world, so objects that can be interacted with, and also to Java adapters, which, as mentioned in the talk yesterday, are created if you, in JavaScript, implement a Java interface or create a subclass of a Java class. And finally, there's the bottom linker. The name is quite apt. It catches all linkage requests that could not be fulfilled by any of the other linkers and will, depending on what it can do, it applies very conservative rules of its own. It will, if it cannot handle the request, it will throw an appropriate exception or will maybe successfully apply the very conservative linkage rules. You are invited to go to the Nashorn source code repository, build your own instance of Nashorn, and then go to JDK9 Nashorn samples Dynalink. This directory is full of goodness. Many examples for various aspects of the Dynalink framework. And in fact, many of the examples I have in this talk on these slides here are from that directory. Just compile everything there and then run with the JJS executable any of the examples. To shed some light on how these details are implemented, I'm now going to walk quickly through an example that adds a .stream property to Java arrays, so that when you use a Java array in JavaScript, you can tell the array .stream and get a stream out of it, Java utils stream. Code size okay? Nah, not so. Okay. Good, so this is the overview slide anyway. I'm going to zoom in on all of the details here and briefly talk about all of the highlighted bits in some given order. First of all, those dynamic linkers can be loaded automatically by virtue of exploiting the JDK's service loader capabilities. In this case here, we use a type-based linker. I'm zooming in a bit. A type-based linker because it should respond to certain types only. And the types we want to respond to are array types, as we want to add this .stream property to Java arrays. The implementation is done in this method here, canLinkType. And as you can see, what it does is it simply checks if the type that's coming in is an array type, and if so, it will return true, if not false, and then the linker will pass on the request to the next linker in the chain. The guarded invocation here in this method implements the operation on the one hand and the cache check on the other. So what we do here is we generate a guarded invocation that will, upon each invocation, check whether the operation can be applied, and then will apply the operation. So if the guard fails, that's a cache miss, so to speak. Finally, unmentioned on this slide, there is a method called array2stream, which, well, turns the array into a stream and then returns that. This is the gist of the implementation. Moving on. The argument of type link request to this method holds all the information about what and where is to be linked. And the method extracts from this request the receiver, then applies the check whether this linker is responsible for the type that it found, and it will then also extract the call side descriptor. From the call side descriptor, the linker can extract the operation, and from the operation, in turn, it can extract the requested property or element, and it needs to check whether the requested element is indeed stream, and because this linker is responsible for generating those streams from arrays, it will only respond to a get property operation with stream as the named operation argument. Finally, we have this guards class that can be used to generate various convenience guards that are commonly used. So in this case, is of class, which checks if the argument at hand is an instance of some given class. And this is in principle what needs to be done to implement this .array, .stream property on Java arrays to be usable from JavaScript. As mentioned, the actual method that does that is not shown. That's not quite the interesting bit here. What constitutes a dynamic linker? The prioritized linkers, so it's three elements that constitute a linker, or that constitute the linker factory. The prioritized linkers are, well, prioritized over all others. They are tried first. Then we have all the linkers that were discovered through the service loader mechanism. And finally, there are fallback linkers. In the Nashorn case, these include the aforementioned beans linker and also the bottom linker. The beans linker, by the way, is the default fallback. As mentioned, it turns property accesses into things that work if the target object conforms to the Java Beans conventions. So, for instance, an access of the form obj.color will be turned into an object getColor invocation if that is available, or into a field access, whatever the public property, the publicly visible property is. The fine print. Beans linker is pretty capable because it also supports overloading, and that also in the presence of guest language specific coercion rules. It also supports var args, or variable arity invocations. And caller sensitive methods are linked in a secure manner. I mentioned this yesterday in the Nashorn talk already. For completeness, I will reiterate briefly. So caller sensitive is tricky because the lookup context is relevant. Dynalink uses method handles and normally applies public lookup. But caller sensitive will typically expect other lookup contexts to be at the call site. And Dynalink takes care of transporting the call site lookup object through the entire framework and into the caller sensitive method so that the context of the actual call site will be applied rather than the context of the method handle that was generated from Dynalink. A new addition to Dynalink in JDK 9 is dealing with missing methods. It resembles very much the way that Smalltalk uses. So when you send some message to an object and the object doesn't understand the message, then it will invoke the method called messageNotUnderstood, and any class implementing this method can deal with it. The default behavior is to pop up a debugger window, but I digress. This isn't about Smalltalk. So in any case, Dynalink now also offers such a messageNotUnderstood equivalent, and it is entirely controllable by the language implementation. So roll your own. Security. If code wants to get hold of The lookup object or linkers should be automatically exported. Permissions have to be set, and because these operations deserve some attention. I'm not going to go into much detail about this one, just as a remark. By this, I can conclude the overview and move to advanced topics. This took me 30 minutes, so maybe we will not be able to cover the more advanced topics, or I will be very quick. We will see. So I promised to take a look at a somewhat larger scale example, and that is a Jython linker built by Sundar. You should look at everything on Sundar's blog because he keeps generating goodness. Just go look at the stuff he publishes. It's always good. Now we're going to look at the Jython example. Code size okay? Yeah, okay, yes, no. Okay, I'll zoom in on the relevant bits as usual. So here's the code on this slide is actually JavaScript, but the red part is all Python. It's in the same file, and that is possible by virtue of a here doc. When you start Nashorn in scripting mode, you can use this here doc syntax, and it will take everything until the closing bit as one big string. So what we do here is we send an entire chunk of Python code to the eval method of a Jython engine. What we do next is we get some data from this Jython engine and then all in JavaScript access some of the properties on that point object and invoke some methods on it. So we have a little example of language interoperation here. This slide briefly illustrates how to use such a linker by just adding the jar file with the linker to the class path. Thanks to the service loader, this linker will be automatically loaded. And the contents of that jar file are not so much. It's really just the classes and the manifest describing what services are offered. A snippet from the source code of this linker. Some aspects of what's needed to link these property getters for Jython from Dynalink. You can see some handle constants at the top. For getting an attribute, that's the PyObject getAttr. For translating an object from Jython to Java, that's the Py2Java handle. And for checking whether an object is a Jython object, that's the isPyObject. Then on the lower half of the slide, the guarded invocation is created from a named operation. The name is bound to the Jython getAttribute handle. The result is converted, thanks to filter return value, to a Java object. And finally, the invocation is guarded with the isPyObject guard. And consequently, it will not be applied if the target is not a Jython object. So much for Jython. More examples. As mentioned, the samples directory is full of Dynalink examples. This one is about XML DOM linking. If you look at the code down here, you can see that, again, we are using a here doc to generates some HTML, and in that here doc we use variable expansion or expression expansion to insert some computation results. The RSS object is the document element, a DOM tree, and any property access that begins with an underscore is treated accordingly by the DOM linker. So we can get access to the document object's channel element, then to that element's title element, and then to the content of that. And the result of that is inserted here in the HTML code, and so forth. Okay, to summarize the custom linker advantages. Custom linkers support implementing, so to speak, embedded DSLs on alien objects. Alien from the perspective of the Dynalink application, in this case NASON. And those alien objects don't even have to know. We have also run a little experiment for databases and result sets. And this experiment works like this. You have a database connection, JDBC database connection, dot table name, dot filter, and then a JavaScript function. And this can be used internally to generate a SQL query that will then be executed and return a result set. The result set can be dealt with using a linker equally well so that it mimics a list, and so forth. The opportunities are endless. I've made it to the more advanced topics. Hold tight. So Dynalink does not only enable some flexibility in language implementation, as seen, it also allows for very, very fine-grained control over details of the linking process itself. The linking process consists of several sub-steps, each of which can be controlled to some degree. And these methods here on this slide represent the API entry points for exacting this kind of control. This is the control flow of the linking process internally. The steps are applied in the given order, from top to bottom. What happens observably from a distance is you call dynamiclinker.link, and in the end, some call site.setTarget is done to link the call site. The one thing that is commonly under control is passing a link request to known guarding dynamic linkers and decoding operations. Also, type conversions are commonly applied as required by the language implementation at hand. Most of the other things are hooks for more advanced language runtime mechanics. First of which, the auto-conversion strategy. So the call site type and method handle type may have to be matched. There may be slight mismatches in the types. Dynalink automatically does this for all the coercions defined by the Java language specification and also for custom type conversions defined by linkers already. Sometimes though, even the standard JLS coercion rules need to be customized. And such things can be plugged into the linking process here. NASON makes use of this capability in unboxing null to primitives. So in JavaScript, you can write these strange things like 7 plus null. And this is where the null will be converted or coerced to the right type and value. Internal object filters. A language runtime should avoid internal objects leaking to the outside world. No, not should, must. Nashorn internally uses, for example, a class called cons_string for delayed concatenation of strings. And also, the internal representation of a JavaScript object is called script object. And those are not supposed to be observable from the outside. So it must be made sure that these don't escape, and this phase of the linking process can be used to ensure that these objects never escape from a Dynalink call site. Nashorn uses this to collapse cons strings into strings. So it enforces the toString operation on those delayed concatenations. And also to wrap script objects into JS object instances. And JS object, as mentioned, is what a JavaScript object looks to the outside. Pre-link transform. This almost last step in the linking process is given the final chance to transform a guarded invocation's method handles before linking them to a call site. Guarding dynamic linkers shouldn't apply non-JLS type conversions on method handles return types to match them to the call site type. This should rather be left to the pre-link filter of the runtime owning the call site. This ensures the correctness for runtimes with optimistic typing, and this is what it's used for in Nashorn, even when linking handles from some foreign linker into its own call sites. Okay, so these are not so commonly used. I'm almost in time. Last slide. Dynalink is part of JDK 9 in a dedicated separate module. The source code lives in the Nashorn repository of the JDK 9 forest. There are many examples there. There's Javadoc, and also, again, watch out for posts in Sundar's blog. He already has a sizable amount of very interesting examples described at very good level of detail there. And also, if you have questions, ask them on Nashorn Dev. Attila reads there too, and will be happy to answer questions. So will I, if I can.